Oh, it's got a level on it, huh?
Our project was an autopilot for a remote controlled airplane. We designed it to, you install it between the receiver from the transmitter that you normally use to control a plane and the servos that control the wing surfaces here and the tail surfaces. And it has sensors on board, and it runs a program, takes data from the sensors, interprets it, and controls the surfaces in order to do certain things. It's based on an Arduino microcontroller. It's actually an Arduino Shield, if you know, heard of that. It plugs into the top of one and holds all of our sensors. And
here's our, first we do the hardware design, and then we define like what we're going to do on the project, and we set up the goal that we want to do, and then we create the outline, and then we drew the block diagram for the project to see like, and then we choose the project device that we're going to use on the project, and then we putting everything together for the project.
software, I wrote a program for each function that takes a sensor input and converts it into the control output. All the functions run at the same time. You can select between them with the transmitter, and tested it without flying it to make sure that all the functions work the way we want them to. Like I said, it's an autopilot. What it can do, it can hold. We didn't actually manage to do bearing hold. It can do It can hold the wings level and hold the pitch. And it can also maintain the same altitude. The basic aerodynamic functions of a plane. There's these are the ailerons. They move in opposite directions to bank left and right. This is the elevator. It goes up like that, pitches the nose up, and vice versa. This is the rudder, which controls the yaw.
And here is the diagram that we put in. Here's the diagram that we put inside of the plane, and then we connect the remote controller receiver into the Arduino, and then we send in the signal from the receiver.
The signal comes from the transmitter to the receiver, and sometimes if it's running a program that contradicts what it's being told to do, it will ignore the input. But in every other case, it passes the signal straight to the control surface servos. The motor speed controller is hooked up, but we didn't actually use it because we don't have an airspeed sensor. We ran out of money for that and other things. So in theory, we could also control the speed of the propeller, but we don't have any sensors that would make use of it, so we didn't do that. The main sensor we use is the accelerometers. And we program the Arduino over USB from the Arduino IDE.
Here's our device for replace for the block diagram, and here's our sensor, two sensors, and the receiver and then transmitter, and there's the connection of the whole circuit, and here's the list of the device name. First, we're going to talk about the remote control plane. The plane package comes with the servos and the model and servo. Each servo is attached to a road and control. Sorry.
Each servo is connected by a metal rod, either these little ones here or these ones that run the length of the body to the control surfaces. Go to the next slide.
And here's our motor. It's 3-phase, and it's run about like 13,
13.
it's 1300 RPM per volt. And then it's 3-wire, 3-phase. One is for ground and one is for load.
No, there's 3 separate coils, and it alternates power between them. It sends a pulse to each wire in turn to spin it.
And next is our microcontroller, and it has 14 digital input. It has 14 digital pin. It can be used for input or output, and then also it can use for the pulse width modulating output, and it also have the one USB port in here, and then we have the power jack to use for power supply, and then we have the transmitter, receiver, and power LED. And here's more detail about the Arduino pin now. And then in this line, this table describes what pin that we have. We have reset pin, voltage pin, and then voltage from 3.3 to 5 volts. And then we have 2 ground, and then we have 6 of the analog input. And then here's the table, so the right side of the pin. So all the digital pin.
We didn't use any analog.
Yeah.
We used ground and 5 volts. We had to use pulse width because that's how servos are controlled. So we used pins 8, 9, and 10 for the 3 control surfaces, and pins 1 through 5 for receiving signals from the receiver.
As the motor speed controller that we use to control the motor, and then we also use them to bring down the voltage to supply the motor, and it also connect to the receiver, to the channel 3 for the rotor, to control the speed of the motor. And here's our sensor. This sensor allow us to do the raw linear oscillation and the rotational velocity. And then here's the pin that on the sensor. And we're going to use the I2C series clock and the series data pin for the.
It has 2 I2C buses, a master and a slave, and we only used a slave because if we had all of our sensors as slaves to the Arduino, we didn't use these or a clock. We just used the 2 I2C pins plus voltage, ground, and VIO to specify that we were using 3.3 volts and not 5.
And here is another sensor that we're using to measure the pressure between 30,000 to 1100,000 Pascal. And here's the pin that on the sensor, and also there has the pin for the serial clock and serial data. And we are going.
We use the same 4 pins.
Yeah, we we use the same part again, just looks like the last sensor. And then we also connect to the VCC for 3.3 volt and the ground, and these two pins, we're not going to use that. And we also using the remote control transmitter to control the sending the signal to the receiver. And here's the control stick for the rotor, and here's the for the Orion, and this one is for the rotor operator. And here's the switch for the gas switch.
This is what we use to select functions.
And the remote controller receiver have 6 channels. We're going to use channel 1, channel 3, channel 1 through channel 4, and channel 6. And then the receiver is powered up by the speed controller. And then the receiver get the signal from the transmitter is the pulse persistent modulation is PPM signal into the into the pulse rate modulation signals, the channels.
Battery.
Oh, sorry. And also the battery, we bought the battery is from 9 volt to 12.6 volt. It's nickel type.
So it's written in C using the Arduino IDE. We said we created routines for each autopilot function. It's selected by one variable input on here, the dial, so different areas on the dial are different functions. We use to control the sensors and to run the I2C buses, we used open source libraries. Somebody had already written for those sensors. The pulse width modulation read function, because we get pulse width modulation from the receiver that would normally control the servos. We have to read that and take that into account. The read function on the Arduino is jittery. It's not consistent. It seems to be an inherent problem with the Arduino. There's nothing we could do about it other than debounce it. So I have it set up to read. It reads. It keeps track of the previous 3 and uses the average, which helps. But you'll see when I demonstrate it, it's still a little jittery. I had to choose between having it be jittery like that or have really low control resolution, so it would only move in 4 steps or something. So this seemed to be the best balance. For verification, uploaded the final program onto the Arduino, assembled it, put it all inside, and tested it to make sure it did what we wanted it to do for each function.
Here's our timetable that what we schedule to do is thing. And first, at the beginning of the semester, we still doing the research and then from February 10, and we order the equipment online, and then after we get the equipment, we test each hardware to make sure everything is work, and then we
spent a lot of time figuring out the software, and let's see, verified it, prepared the report, and presented it. The total cost was about $250. There's the breakdown of it. The sensors were the most expensive part. We bought a magnetic sensor that we didn't end up using because the data that it produces would have taken quite a bit of work to turn into something useful for us, and we ran out of time to do that. The transmitter and receiver, it's all really relatively cheap. Engineering constraints, safety, it's soft and lightweight, it's not exactly dangerous, but the propeller does spin really fast, which I'll show you later, and would do some damage if you touched it. Manufacturability, I did it on a perf board, I think it's called, but it could all be put on one PCB if we designed and ordered one, including the components that we mounted on, and probably the processor itself, so we wouldn't need the Arduino, we just use the Atmel ATmega 328 or whatever it is. All of the parts are very readily accessible, and none of them cost very much. The most, like I said, is that sensor, which is $40 for one, but if you bought them in bulk, they would be cheaper, probably about $25. Sustainability, it's polystyrene, it's fragile and can't be recycled, so that's bad. But the electronic components are almost all ROHS approved, which among other things means there's no lead in them. So apart from the solder,